Here, Fabio Poisi. Dr. Fabio Poisi is a senior researcher at the Fondazione Bruno Kessler in Italy and a co-investigator at the Italian Institute of Technology. He received his PhD in electrical engineering and computer science from Queen Mary University of London in March 2014 and has been a postdoctoral fellow in European Union project for nearly 3 years. During his tenure at FBK, Fabio participated in a number of EU projects, including H2020 Replicate EIT UAV Retina, H2020 MIMAX, and many others. He's currently the principal investigator of GPI Shield, and he has extensively industry university research experience in the field of multi-object detection and tracking, human behavior analysis, 3D reconstruction, and scene understanding, 6D attitude estimation, robot navigation, machine vision, and augmented reality. He is also responsible for several industrial projects related to machine vision and augmented reality applications. He also serves as regional chair of IEEE ICRP and guest editor in several peer-reviewed journals. And the title for his speech is Deep Machine Vision for Digital Industry. Okay, let's welcome Fabio Poisi.
Thank you very much. Thank you very much for your introduction. Yeah, so today I'm gonna present this set of industrial projects that we are carrying out in Fondazione Bruno Kessler. But just before going technical, I would like to introduce Fondazione Bruno Kessler, so FBK. FBK is a non-profit public research organization that is based in Trento and is composed of 11 research centers. There are more than 400 researchers in FBK and more than 140 international PhD students. So Trento is located in the north of Italy and in particular in the heart of the Dolomites. So it's a beautiful place if you want to spend your vacation. FBK has 3 main locations. So in the city center, we have 3 centers. We have the Evaluation of Public Policies, the Center for Religious Studies, Italian and German Historical Studies. Then we have another side where you can find the Center for Theoretical Studies in Nuclear Physics. And then on the hills of the city, you can find the technological side where you have the centers like the cybersecurity, digital society, digital industry, digital health and well-being, health emergency, sustainable energy, sensor and devices. And in particular, in my case, I'm from the Digital Industry Center. So my lab is called Technologies of Vision Lab. We mainly do research on computer vision and in related areas like camera systems, machine vision, visual machine learning, deep learning, and extended reality. And these are the current members of the lab. So in today's presentation, I will introduce how we perform visual explanations using neural networks. And in particular, I will show some examples where we use neural networks for quality control. Then I will describe to you how we disentangle visual tasks in order to solve much more complicated problems for industrial applications. And in particular, I will show you 2 use cases. The first one is about smart retailing, and the second one is about automated pharmacy. And then at the end, towards the presentation, I'm gonna talk about the conclusions. So in computer vision, we process images, and images is an image is a collection of pixels, and each pixel is composed of 3 values, which is the red, green, and blue. So we have this big tensor of number, and these numbers are those that we process in order to extract the information from the images. So with a neural network that we use for classification, so let's say that we have this image, and then we give the image to our neural network, which is a highly parametric function that we have to learn. So we have to train our neural network in order to learn the parameters of this function. Neural networks are divided into layers. It can be arbitrarily deep based on your problem. And the problem of classification is to find a distribution over the classes that you want to classify based on your image. So like in this case, we have 5 classes, and this neural network says that the dog class is the most likely to be the one represented in the image that you gave as input. The software, the algorithms that we use for training these neural networks are called backpropagation. So because these neural networks are highly parametric, so they have potentially millions of parameters that needs to be trained, it's very difficult to understand sources of errors in case of some probably mistakes. So people develop some tools for debugging the neural networks, and GradCam is one of the approaches. So let's say that you have this image, the neural network said that is a dog. So you can backpropagate this information in order to produce the gradients. And when you combine gradients with the activations that the neural network produces, you can see where the network is actually focusing. So you can see the most with the higher intensity activations in this image. And in this case, the activations are focused on the object of interest. And the more you move close to the image in the neural network, the more the attention focuses on the structural elements. So we use these tools for debugging our neural networks when we have industrial projects. So here we have, I want to show you one industrial project. So in Italy, you know, we are very famous for wine. So we have this company called Cavit, which is a company from Trento. And Cavit wants to use a system to automatically determine the quality of this grape. So the one that you see in the image is actually grape. And at the moment, Cavit has an operator that visually inspects the grape. So we have the farmers that they bring the grape to the winery, and the operator says, okay, this grape is of a certain quality. But Cavit wants to have a system that automatically grades the quality of the grape. So we have a bunch of images. We use images to train our neural network. And our neural network, over here you see, it takes as input the image of the grape, and it says, okay, probably it's of either grape A, B, or C. A is the best, C is the worst. So in this project in particular, we had fairly, I would say, bad results. So we were not able to understand why the results were so bad. So we checked the GradCam, the one I showed before, and we noticed that actually the attention of the network was focusing on the background. So it was not focusing on the grape. So it made us like perform some more further analysis, and we understood that the annotations that we were given by the operators were not that accurate. So we are now in the process of refining the methodology to collect annotations. Then there is another project, is about to determine the quality of the cheese. So also in Italy, we have many cheese. And Trentin-Grana would like to develop an automated system to assess the quality of the cheese they produce. And one measure to determine the quality is to measure the thickness of the crust of the cheese. So they would like to have an automatic system that tells them, okay, this cross is of a certain thickness. So we develop a neural network, a simple one, that we give as input a patch, like a crop from the image of the cross, nearly the cross. And the neural network needs to regress one number, which is the thickness. So here, instead, we had really excellent results. We checked the attention, so by using GradCam, and we actually noticed that attention was focusing on the part of the cross, which is exactly what we wanted. So it means that the network is trying to use that information in order to perform the regression. And this is actually what gave us a good score. So with neural network, tasks can be also a little bit more complicated. For example, if we want to perform detection, so it means locating and classifying objects in an image. If we have an image here, detection allow us to determine this bounding box inside the image that tells us that here there is the object of interest. There could be also several other objects, so the networks can detect multiple objects in the image. But for sake of simplicity, I just put one here. So this bounding box can be defined by a center, a width, and a height. And the neural networks can be something like this. So we have a part that is that we typically call backbone, that is shared among these two branches. And you have the top branch that is in charge of classifying the object and determining the center. The other branch is instead in charge of determining the width and the height of the bounding box. So you start seeing here that things are getting a little bit more complicated. And when we have to debug these particular networks that have millions of parameters, start becoming challenges. So in case of errors, which part of the neural network can produce the error? Is this part related to the classification? Is this part related to the regression of the center? And so on. And what about the backbone that is shared? Is this the cause? So things are quite complicated. So as I said, it's difficult to debug errors in these multitask neural networks. So for industrial projects, we want instead to have full control on our pipeline. We would like to be able, given a visual task, to analyze each subtask independently. So if we split this visual task into subtasks that are of a smaller difficulty, probably we'll be able to assess better the performance. In fact, we can have subtask 1 that is performed with one neural network, which is independent from the other. Subtask 2 can be an independent neural network that takes, for example, the output from subtask 1 and it produces its own output. Perhaps subtask 3, it's easier and can be developed with traditional computer vision approaches like handcrafted, or could be a combination of both, and so on. So in this way, we are able to really control our problem and to debug block by block. And potentially we can have people, separate people, working on separate subtasks. And this is much easier for us to develop application, have the full control. So now I would like to show you one use case where we apply this concept to smart retailing. Here you see a European project where the goal is to build a fully automatic and smart micro market. So you have a person that enter in the micro market. There is no cashier. There are, however, a lot of cameras that try to understand the behavior of the client. The person can take the product and the product will be automatically added to the shopping cart. And if a person re-put the product on the shelf, that will be, of course, removed. Then once the client has done, it gets out, and then the payment will be directly added to the account of the user. So this is a European project with several partners. But as you might imagine, it requires a lot of technology related to vision, to understanding the behavior of the user. And here I would like to talk about one module that we developed. That is the module that needs to understand when a client gets an object get a product from the shelves. So here, the first task that we want to develop is to detect the hand that is holding the product. So we have a neural network that, given an image, performs only hand detection. And here you can see some results. So as you can see, the network is focusing only on the hand that has the products, that is holding the product. The other hand is not considered. In fact, when the user changes the hand, the bounding box will shift to the other hand with the product. So we put all our effort in developing only this thing. And now here we don't know the product that the user is holding. We only know that over there is a product. So the second step is to extract a crop, like a patch from the image, and transform that image that is probably, I don't know, a few thousand pixels in one representation that is a few numbers, like 512 numbers, that is highly discriminative. So we have this independent neural network, which task is only to create very discriminative representations of these patches. So we do this for all the products. And in fact, if you see here, we have so many products, we can see that in the feature space of our patches, we can see that there are small clusters here and there that are identifying each product in the feature space. For example, that cluster of points are the representations of our patch of this product, of the chocolate. So you can imagine, like, if now we have a new patch that is coming in, I will project this patch in the representation space. And if it is close to that cluster, I will say, okay, this patch belongs to this class. So with a simple nearest neighbor approach, you can determine the class of this patch. And this way of operating is highly dynamic because you know what is happening inside your feature space. You can see that the space is nicely clustered. So you have full control. In fact, if we look at the classification results, we are very, very good. So we managed to have more than 95% accuracy. And as you can see here in this confusion matrix, we have the diagonal that is the one with the highest accuracy, which is exactly what we want. There are very few misclassification cases that rarely occur. So the second use case is about automated pharmacy. And here you can see this company, Riedel Phasis. Riedel Phasis want to build robots that can be put into hospitals or pharmacies, and they handle drug packages. So you have here the storage nicely organized of all the drugs. And when the pharmacist or operator asks for a medicine, for a drug, the robot will go over there, will pick the drug, and then it will deliver the drug to the operator. Here, the problem is the following. So if you put this machine in a hospital where they have to handle thousands of drugs every day, to load the machine in this way is very challenging. It requires a lot of time. So every day, the operator should do something like this. This is currently how they are doing it. So it's very demanding. They would like to improve the way the storage is loaded. They don't want to have the operator that put one drug at a time. So this is currently the bottleneck that they would like to improve. So the project they gave us is to build a fully automated loading system that should have a high throughput, so about 360 pieces per hour. It should be general. So it should also handle cylindrical packages, because the company will also like to target US market, where most of the drugs are served into cylindrical containers. They want to reduce the cost by 50%. They want to have a compact design, and a high reliability with low maintenance cost. So together with the other partners, we come up with this design where the operator can drop the packages inside this loading area. Here you have a robotic arm that replaces the arm of the operator. Here you have the picking platform where all the drug packages will be organized. And here you have a turntable to scan the drug in order to detect the expiry date, because also the database can have this set of expiring dates that the system can also use to organize the material. And then here you have the dropping area where there will be the second robot getting the drug and putting it back to the storage. So in our case, because we work on vision, the focus was on this part. So detecting the drugs on this platform in order to inform the robotic arm where to pick the drugs. So this is a problem that is called Object-6D pose estimation, which aims to detect objects and estimate their orientations and translations relative to a canonical frame, for example, the one of the camera. So here you see that there is this robotic arm. Here you have the RGBD camera. Here you have the working surface, and then you have your target objects and the robotic arm with the end effector should grasp. So the objective of 6D pose estimation is to first localize the object, estimate the pose, determine the grasping points for the end effector, and then perform the planning in order to go and pick the object. In particular here, if you have, for example, this product in the scene, the product lives in its own coordinate system. And then you have to determine the translation and the rotation with respect to the camera coordinate system. And if the camera is calibrated, then you can know the position of the object in 3D and then inform the robot where to do the grasping. So this is our first prototype. So there is a little bit of cardboard here and there, but bear with me. So you have the drug packages that will be dropped inside the hopper. Basically, we have a hopper. And then here you have the conveyor belt that carries all these drug packages to the picking platform. Here we have our RGBD camera that is connected to a computer, so machine. And then we have the robotic arm that needs to be informed where the objects are on the picking platform. So our data engine, so if you consider this, the RGBD images that are captured from the camera, these are given to algorithm to perform object classification and pose estimation. The output of this task will go to the robot to perform the action, but also they will be logged. We have a logger that is often analyzed by an operator. And if there are some errors that occur, the operator can check them, can see that these are difficult cases. So it picks all the difficult examples, it annotates manually the difficult examples, and it adds these difficult examples to the training data in order then to update the models, so that over time, we are able to improve the models of our system with always like more and more difficult examples. So the model will become better and better over time. So now I will focus on this part. So we have our RGBD images that are given to our 3D instance segmentation approach, which is a hybrid between a neural network and traditional approaches. And in particular, we can detect on the depth the outline. Let's say we can detect these objects and be able to discriminate whether they are boxes or cylinders. And then we are able to transfer this information in 3D because we have the depth information so that we can build 3D bounding boxes of our objects. Then the second task, if it is a cylinder, we would like to know the position of the cap. So we would like to understand how to place the cylindrical box in the correct position with the cap located on top. So we have a neural network, a separate one, that is in charge of understanding the two potential extremes where the cap could be. Then we rotate the image, we give it to a third neural network, and the neural network will tell us whether it is up or down. So we disentangle this process in 3 different tasks, which they're fairly simple. Like, let's say these two, for example, the 2 last cases are fairly simple. The network is performing very well. And we are now focusing on improving, in particular, this part, in discriminating between boxes and cylinders, and to determine the exact position of the packages. So here you can see some results. So here you see that the position is given to the robot as a point, because the end effector of the robot is a suction. And then in the case of cylinders, the red arrow that is pointing in this direction is telling to the robot that the cap is over here. In this case, the cap is over here. In the case of rectangular boxes, the direction of the arrow is the longest edge of the package. You have other situations like this one, where you have these cylindrical boxes. We also have another step in the algorithm that I didn't show over there that fits a cylinder once the box is detected. This is in order to have like a very accurate position of the grasping point for the suction. And then we have here another case. Here you have another case. Here you have another case where you have the region of interest of the algorithm, and the robot will only operate in the region of interest. And then this one will be processed. This package will be processed later. So here I will show the final product that the company put together, and they showcased it to a big expo that we had in Italy called Cosmo Pharma. Here you see the storage with all the drug packages nicely organized. Here you have the loading hopper. So now the user, the operator, can drop all the packages inside without putting it one by one by hand. You can see that the machine is very big. Over here, we have the picking area that later we will see from the other side. But the design of the system is very compact, the part that is dedicated for the organization of the packages. But the machine overall is very big because it needs to have a big capacity. So from the other side, you have this robotic arm. The system is able to understand when the picking is done from an inconvenient side. There is a logic to reorganize the boxes in order to get them in the convenient side. Then you have the object that is dropped on our turntable. Here the system detects the expiry date of the package. And then we have the second robot that comes, it collects the package, and then it would put it in the storage. The system is also capable of detecting if there are overlap cases like this one, because these cases cannot be handled by the robot. So there is a logic in our conveyor belt that will reorganize the boxes in order to make them more suitable for the grasping. Here you see that the cylinder has the cap located on top because the vision system detected that the cap is on top, so it can be put in the storage in the right direction. And then here you will see on top that there is the next batch that is ready to be processed. This is my last video. Here you can see some more cases where boxes are handled. Here on top, you see how the next batch is getting ready to be picked and processed. And I have to say that this machine was put inside the Expo. It processed around 3,000 drug packages, and it failed very few times, probably I think about 10 times. So it's very reliable at the first stage of test. So in conclusion, I've discussed how we perform visual explanation applied to industrial project. I presented idea how to disentangle visual tasks in order to handle complex industrial projects. I analyzed some use cases, in particular a smart retailing use case and an automated pharmacy use case. And I hope you enjoyed the presentation. And then I'm open to answer your question if you have any.
Okay, thank you very much. Thank you very much for your excellent presentation. And it's really impressive for your presentation about intelligent vision. And I think if you have some question in our conference room, you can talk with Dr. Fabio. Do you have any question?
Hey, Fabio, can you hear me?
Yeah, I can.
I saw you determine the quality of cheese by testing the thickness of crust. I wonder if you did it with the semantic segmentation or just by the image classification task. I don't sure.
Yeah, it's here. So no, we didn't do any segmentation. The network managed to understand where the crust is by just doing regression. So the only task that we were asking to the network is to regress the thickness of the crust, giving a patch. And we noticed that the network was able to understand and to focus on the location of the crust.
Okay,
no
okay,
segmentation was enforced.
Okay, I get. Thank you.
Thank you very much.
Okay, thank you. Do you have any other questions?
Hi, Fabio. Can you hear me?
Yeah, very well.
Oh, hi. Thank you for bringing us so many interesting and meaningful projects. From the grab quality classification to cheese and robotic arm drug sorting. So the robotic arm project cover a wide range of areas of vision, including object classification, post-estimation, and more. So I think there should be many difficulties in the real projects because your project is not only work well on the data side, but in the real world. So what do you think is the most difficult things in your real project? Is the difficult examples, object classification or others? Thank you.
Yeah, so in this particular field, all the drugs are unknown. So we don't have a raw model that we can rely on and search inside the images. We don't have any prior on the shape. I mean, the shape, more or less, we know it. So it's rectangular, like cuboidal for the packages, for some packages, a cylindrical for the other packages, but we don't know the appearance. And the organization of the containers on the conveyor belt is also unknown. So we really had to put a lot of effort in trying to develop something that is generic enough in order to detect things that we've never seen before. And this was the most challenging case. The second challenge is the sensor itself. So here you see the point cloud that is generated from the sensor because we have a RGBD sensor. So we can take the depth, apply the intrinsic parameters, and transform it into point cloud. And there are some boxes, especially the cylindrical bounding boxes, which are semi-transparent. So the ray of the depth sensor, when it hits this type of surfaces, it will be kind of destroyed. So the information that we get back, it doesn't look like a cylindrical box at all. It's something, it's mainly noise. So the combination between RGB and depth was very important in order to handle these situations where the signal was completely destroyed, let's say, by the material of the box that we were detecting.
Okay, so because there are lots of different drugs, so the modeling is difficult. It is.
Yeah, exactly.
Okay, thank you.
Thank you.
Okay, thank you. And Dr. Fabio, I also have a question about your interesting talk about the identification of the goods in supermarkets. So could you could you tell us if there are several people in front of a racket, and maybe their body will shield or cover some goods? How can you identify all the goods in this occasion, or improve the percentage of identification? Thank you.
Yes, so here I show an example where there is one person that is handling, let's say, the product, but the algorithm can detect multiple situations. So this algorithm was trained to detect multiple hands. So if there are more people that are in front of the shelves interacting with the object, the system will be able to detect multiple objects as well. In addition, the system, the scenario that you see over there also has other sensors that are placed on the shelves. So the overall system can reason about these sensors plus the vision part. So by combining different sensors, they're able to reliably understand the person that is interacting with which object. So they can constrain the problem in that location. Also, the people are tracked inside the supermarket. So we know the exact location in 3D where the person is inside the market. So by combining a lot of information, we can reliably understand the behavior of the person or of the people.
Okay. Thank you so much. And thank you again for your excellent presentation.